Hi, I'm Robert Crowe. In part one of this three-part series on sharding and parallelism, we'll explore how to scale your Flax NNX models using JAX's powerful distributed computing capabilities, specifically its SPMD paradigm. If you're coming from PyTorch and have started using JAX and Flax NNX, you know that modern models often outgrow single accelerators. Let's discuss JAX's approach to parallelism and how NNX integrates with it seamlessly. In this episode, we'll cover the what and why of distributed training, introducing the fundamental concepts of parallelism and the core JAX primitives needed to implement them. So let's get started. Why do we even need distributed training? Well, the primary drivers are the sheer scale of modern models and data sets. Trying to fit a multi-billion parameter model onto one GPU just isn't feasible. Distributed training allows us to break down the problem. JAX tackles this with a paradigm called SPMD, for single program, multiple data. The idea is you write your code as if for one large logical device, and the compiler figures out how to run it efficiently across many physical devices. So how do we speed up training when one GPU or TPU or other accelerator just isn't fast enough? Well, let's quickly review some well-known styles of parallelism before getting deeper into how JAX and Flax NNX handle it. A common and fundamental approach is distributed data parallelism, or DDP. The basic idea is to parallelize the data processing. First, we take our model and replicate it, make an identical copy onto each device, which is typically a GPU or TPU, possibly across several machines. We then split the data batch among the devices. Each device processes its unique data slice in parallel, calculating the local gradients. Critically, these gradients are then averaged across all devices. This single averaged gradient updates all model copies identically, keeping everything synchronized. The result? We process data much faster in parallel, significantly reducing overall training time. It's a core scaling technique. Standard data parallelism replicates the model state everywhere using lots of GPU or TPU memory. FSDP improves this. It's still data parallelism, different data per device, but highly memory efficient. FSDP shards parameters, gradients, and optimizer states across all devices. Each device only stores its assigned slice. It temporarily gathers full parameters for a layer only when needed for computation and then frees the memory. This drastically cuts memory usage per device, allowing significantly larger models or batch sizes on the same hardware compared to standard methods. And what if one model layer is too big for a single GPU or TPU? That's where tensor parallelism, a form of model parallelism, comes in. Instead of splitting data, we split the computations within that massive layer across multiple devices. Think of it like several machines tackling one huge matrix multiplication together, working on the same data, but each doing only a slice of the math. This lets us run models with enormous layers, exceeding the memory of individual GPUs or TPUs. However, it does require fast communication between devices. The foundation for explicit parallelism in JAX is the mesh. Think of it as creating a logical arrangement, like a grid, of your physical hardware. We typically give names to the axes of this grid. One common setup is a 2D mesh with data and model axes. Data often refers to devices used for data parallelism, and model for model parallelism. This mesh object becomes the reference for how we'll distribute our tensors. Here's a code example. It's showing a mesh with 8 devices in a 4x2 grid. You might use this with a V28 TPU, for example. Once we have a mesh, we need a way to specify how a particular tensor, like a weight matrix or an input batch, should be laid out across that mesh. That's where partition spec, often imported as P, comes in. It's a simple tuple. Each element corresponds to a tensor dimension. You either put the name of the mesh axis to shard along that dimension, or none to replicate along that axis. An empty P means the tensor is fully replicated everywhere. Here are 3 code examples showing both sharding and replication across 2 mesh axes, data and model. A named sharding object simply bundles together a mesh and a partition spec. It fully defines how a tensor should be distributed. The key function to apply this sharding is JAX.devicePut. You give it your data, often starting as a NumPy array, and the named sharding object, and JAX handles moving the data to the accelerators and arranging it into the specified shards. This is crucial for getting your input batches ready for a distributed training step. Here's what it looks like in code. We create a named sharding using a mesh and a partition spec, and then we use JAX.devicePut to actually distribute the shards. The magic of SPMD happens largely within JAX.JIT. When you JIT a function and pass it the sharded arrays like the output of JAX.devicePut, the XLA compiler analyzes the operations and the input shardings. It automatically parallelizes the computation, figuring out which part runs on which device and inserting necessary communication, like all reduces for gradient aggregation. Sometimes you need more control inside the JITted function. JAX.lax.withSharding constraint lets you tell the compiler, ensure this intermediate result has this specific sharding. This is useful for performance tuning or ensuring correctness. You can learn more about JAX and the entire JAX AI stack with these coding exercises, quick reference docs, and slides. To watch the whole Learning JAX series, check out our playlist on YouTube. There's a growing community for JAX, and here's the invite link. And here's some links to the docs for JAX, Flax, and the JAX AI stack. So, we've covered the core concepts behind distributed training and the fundamental building blocks JAX provides: the mesh, partition spec, and JAX.JIT. We now have the tools to describe any hardware layout and tell JAX how we want the data arranged. But how do we apply these powerful primitives to our stateful Flax NNX models? How do we embed these sharding instructions directly into our neural network definitions? And most importantly, how do we initialize a massive model across many devices without running out of memory on a single accelerator? Coming up in our next episode, we'll bridge the gap between JAX's functional world and NNX's object-oriented world. We'll dive deep into the main event, the workflow for annotating sharded metadata directly onto your NNX parameters, and the critical pattern for safely initializing a large sharded model inside a JIT compiled function. Don't forget to hit like and subscribe, and I'll see you in the next episode.